So this session will be up to 31st January. So another week also the live session will be there.
Ma'am, I have seen up to 6 Feb to 11, I think.
Oh, so they might have updated, I think, because
Yes, ma'am, updated.
yeah, yesterday I checked, it was not there. Okay, I think I should just share and start because I want to revisit the concept of microstate, and there are two type of question that comes from that topic. So I will share. So a little introduction. I am Anjali Negi. Currently I am doing PhD in IIT Kanpur. So let's start the session. Hello everyone. In this video, I will be solving GATE 2020 chemistry question. Question number 18. They state that the maximum number of microstate for D2 electronic configuration is. Before solving directly the number of microstate for D2 electronic configuration, I would like you to introduce the concept of microstate, how it emerges, and the reason. So let's have a look on the concept of microstate. So this comes from the optical absorption spectra, uh, also known as the electronic spectra of the coordination compound. I take the example of hexa-aqua nickel 2 plus complex sign. It is an octahedral D8 complex sign. So according to ligand field theory, the metal d orbital in an octahedral field T2G and EG, and so that in for this complex there are 6 electron in T2G and 2 electron in EG. So LFT predict that the number of electronic transition will be 1, but we find that the absorption spectra is way more complex than the expected. So instead of a single absorption band, we get multiple absorption band. So here LFT is unable to explain this. So the key points here are that the LFT from ligand field theory, we expected only one absorption band, that is one electronic transition, but through experiment we get 3 absorption band, and the reason behind this was that the LFT assumes that there is no electron-electron interaction. However, this cannot be possible as the electrons in d orbitals have repulsive interaction, and hence it affects the energy overall. So what happens when the electron-electron interact? So let's again take one simple example of D2 ion in octahedral ligand field. So we can take a lot of example. For example, this I am here. It is shown for excited state for the same D2 ion, but when it was in ground state, these two electrons can be in any two orbital of T2G, for example, XY and XZ, or it can be in XZ or YZ, or in XY and YZ. So there are again number of microstate possible in ground state itself, but let's just discuss to an excited state example. So if I am saying that in ground state my two electrons were in XY and XZ, so in excited state, the transition from T2G to EG can happen in two different manner. For example, my XY electron goes from T2G to Z2, okay, and for the same transition, uh, my instead of my XY DXY electron, my D XZ electron jumps from T2G to EG of EZ2. Okay, so there are in total I have only depicted two microstate with different energy for the excited state, for one of the excited state, we can say. So now, according to ligand field theory, it says that both the excited microstate have the same energy. But however, this is not the fact. The fact is that these two microstate corresponding to the excited state have different energy. And this we can actually simply understand by understanding the orbital associated with these microstates and filling up their electronic density. So, for example, if I choose microstate 1, so the electron density will be such that, yeah, so this dz square, okay, sorry, yeah, and for green, for T2G, it is in XZ plane. So XZ is this plane. Okay, so this orbital will be filled. So this is how my electron density looks like for microstate 1. And again for microstate 2, and the T2G XY. So XY plane, yeah, this. So this orbital DXY will be filled. I mean the electron density here. So you can just see that these two microstate 1 and 2 have very different electron density and therefore these two different microstate have different energy because the electrons in d z square and d either xz or xy, they interact very differently here. So the complex that will observe to depict these transition will absorb different wavelength of light, and this is actually contrast to what ligand field theory predicts. So to find out the total number of absorption bands, we have to predict the total possible microstate for the D2 ion configuration, for example that we have taken. So here a group of microstate, actually I can just write here. So a group of microstates with the same energy is called a term, and the number of electronic transitions can be predicted from the number of terms. Okay, so yes, coming to the what this electron transitions gives us, that the quantum number which determine how the electrons interact. So the energy of the microstate depend on these quantum number, for which are ml and ms of each electron. This is called the Russell-Saunders coupling of electrons. So what are ml and ms? So ml is the magnetic quantum number of a single electron, and it goes from minus L to plus L. And capital ml is the total orbital angular momentum for total number of electrons. So this is, we can actually calculate as the sum of magnetic quantum number of single electron. and the maximum total orbital angular momentum ml, capital ML value is actually correspond to the quantum number capital L. And this capital L is the total orbital angular momentum quantum number. So this is the quantum number associated to ml. And the microstate in terms due to the angular momentum, we can just write it as 2L plus 1. Okay. The quantum number capital L that we have seen alone does not define the term. So in addition, we must also consider the interaction of the spin of the electrons. For that, ms is the spin quantum number of a single electron, and the capital ms is the total spin angular momentum. So it can be calculated as the summation of spin quantum number of each electron. And the maximum ms value is equal to the quantum number associated with it, which is capital S. And this quantum number is the total spin angular momentum quantum number. And the microstate in the term due to spin is simply 2s plus 1. Overall, the microstate from L and capital S, we can write it as the product. So it is product of 2L plus 1 and 2S plus 1. Now, to calculate the microstate for free D2 ion, for D2, this D orbital here, you can see just the depiction. So we just have to first obtain the total angular quantum number and total spin quantum number. Okay, so we need to find out ML and MS and then the corresponding quantum number, that is capital N and capital S. So that is, here is that ML for D2 is simply the summation of ML I, which is ML1 plus ML2. And this ML1 and ML2 can have actually the value from plus 2 to minus 2 and ML2 again plus 2 to minus 2. So for ML, just the summation, so it will also goes from plus 4 to minus 4. So the maximum maximum value of ML is plus 4. So my L is actually 4 here, correct? And the MS is the summation of MS1, MSI, which is MS1 plus MS2. And this can have the value from plus half to minus half, so that my MS become my total spin quantum number is plus 1 because it is the maximum of MS. So my S is plus 1. And my MS goes from plus 1 to minus 1. So the microstate for a free D2 ion. So the possible microstate and the overall number of microstate for a free ion with D2 electronic configuration. So we can express it in a microstate table. So here you can simply just do ml slash ms. So your number of or vice versa. So you can just define your table by yourself. So here to define the columns I am using ml, and to define the rows I am using ms. So for D2 we have ml going from plus 4 to minus 4 and ms from minus 1 to plus 1. And so it is simple, just here the possible number of microstate corresponding to ml minus 4 and ms minus 1. It is actually not possible due to Pauli's exclusion principle. And this is that ms value minus 1, meaning my ms1 plus ms2 should be minus 1. That is, both of them should be of same spin, minus half and minus half. Also my minus 4, so this my minus 4 gives me the ml value minus 4 here. So this just two electron cannot be in the same orbital with the same spin. This it cannot disobey Pauli's principle. So therefore here there are zero microstate, and similarly zero microstate not possible in this column, this space of ml value plus 4 and ms value minus 1, and same with the ms plus 1. We have not no, microstate not possible here too. And the other space, for example here, the ml value, which so here the l value, you can see that m l1 is, for example, 2. So my m l2 is minus 1 here. So both of them can have the summation of minus 2 plus minus 1, giving me minus 3, and with the spin of minus half each, so that they are following Pauli's principle, and therefore there are number of microstate is actually 2 1, sorry. Yeah. So again, similarly, if we go on filling these, so you can see that the maximum number of microstate is in where ml is equal to 0 and ms equal to 0. So there are a total of 1, 2, 3, 4, 5 set of microstates, making 5 terms. Okay. So in total there are we get a overall number of microstate in this table. We arrive at the number of 45. So for D2 we get a total of 45 number of microstate. So this goes with the formula number of microstate n factorial n minus r whole factorial r factorial, where n is the total number of electrons orbital can accommodate. So for the case D2, my total number of electron that D orbital can accommodate is 10. So it becomes 10 factorial upon 10 minus number of electron. R is just the given number of electrons. So it's 2 whole factorial and 2 factorial. So this will give me the value 45. For this formula, this is actually the number of microstate. This is based on the term symbol that we are given, because as D2 have a total of 5 terms. So term symbols. So for each term symbol, we can find the number of microstate associated with it using this. And for all those 5, if we sum all these up, then we get a total of 45 again. So for reference, you can check out the book Coordination Chemistry by Ajay Kumar, and for NPTEL reference, you can check the video lecture from NPTEL, Optical Spectra by Professor Debashish Ray, Department of Chemistry, IIT Kharagpur. This is the link for it. Thank you.
Yeah, so if you have any doubt, you can ask. So So, in continuation with the topic of microstate, let's solve another problem. Okay. So this is from GATE 2014 chemistry question number 37. So this question state that the number of microstate in term 1G is. So here, as you have followed the previous lecture, we have just seen that there are two. Basically, we went through the topic of concept of microstate, and then for the calculation, if we get the electronic configuration, we have one particular set of equation to solve, where I can directly put the number of electron n, and in the second part where we have another set of equation where actually I can get the number of microstate for my given term symbol. So here, as I have given 1G as my term symbol, so I will be solving it by using this particular equation, which was 2L plus 1 in whole bracket multiplied with 2S plus 1. Okay, so this equation for my 1G, so let's solve it. So we will get that for 1G, since my L will be 4, correct, and since 2S plus 1, as I can see here from my term symbol, it is equal to 1. So the number of microstate will be calculated as 2 into 4 plus 1 into 1. That will give me 8 plus 1 into 1 is equal to 9. So yes, so the correct answer for the number of microstate in the term given 1G is 9. So you have any doubt? Okay, so let's move ahead. So we have another problem. So this is from coordination chemistry. So it's GATE 2014 again, chemistry question number 39. This question state that among the following, the complex ion that will show strong Jahn-Taylor distortion is. So we are given with 4 different complexes, and we need to find out the correct option which will be showing the strong Jahn-Taylor distortion. Now, before moving into the Jahn-Taylor distortion, let's quickly go through the concept of it. Yes, so okay, so Jahn-Taylor distortion is also, we can call it as a geometric distortion. So what it does is that it reduces the symmetry of my complex or my molecule, and the energy is also reduced in that process. The example of this is the metal complex, for example the octahedral complexes, where either the elongation or the compression of the Z ligand bonds are seen or observed in the given complex. So for example, in the given complex, let's say we have octahedral complex. So in the first case, as you can see that along the Z axis, say this is my Z axis, so along this axis there is a elongation of the bond. Okay, and so we say that this is a axial bond elongation, and we say that this is the case A. And in the case B, we observe again that there is a compression along the z-axis, or these axial bonds are compressed, which in turn elongates the other 4 bonds which are on the xy plane. Okay, So these are the two phenomena which we observe in our octahedral complex, and these are the consequence of the reduced symmetry and reduced energy or the geometry distortion. Now to understand that why this happen, let's uh, go with the theorem given by Hermann Jahn and Edward Teller in 1937. So I will just write it down that in 1937 Hermann Jahn and Edward Teller, they postulated a theorem stating that that the stability and degeneracy are not possible simultaneously unless the molecule is a linear one. So since we are not dealing with a linear molecule, we are dealing with metal complexes which are octahedral or tetrahedral. So here this theorem holds good, where it states that the degeneracy and the stability do not go are not possible simultaneously. What does it mean? It means that since you have already studied that there is a splitting of d orbital when the ligand approaches the metal orbitals, d orbitals, correct? And that splitting, before that splitting of the d orbital, there is a degenerate 5d orbitals present in some energy level. So what I'm talking about is something I can just draw. So this is my degenerate d orbital. Now this degenerate d orbital will split into two different energy state. So this will be Eg and this will be T2G in the case of octahedral field. So this is the concept that I think we are already aware, and so I am just briefly going through what is the Jahn-Taylor distortion. So this is what Jahn-Taylor stated in their postulate, that the degeneracy, so this degeneracy and the stability, they will not go simultaneously. So that is why the splitting is happening there, and this splitting also reduce. So basically this splitting of the 5d orbital will decrease the symmetry, okay, and also the energy will also decrease, okay, for some orbitals. Yes. Okay. So it's only like this, that in the octahedral complex, so basically either the elongation or the compression of the Z ligand bond is observed, and that is what we have shown in the figure A and B. Okay, so let's just go through the case of elongation. So for the case of elongation, I will quickly go through what happens here. So since let's start from, we have our Eg orbital and we have our T2G orbital, okay. So this is a octahedral complex. So this is the energy scale. So in T2G we see that this is dxy, dyz or dxz. Okay, and this is dx square minus y square, and this is dz square. So if I just simply draw a small diagram, so what I will draw that this is something like this, where these are my x and y and this is my z. Okay, now in the case of elongation, so Jahn-Taylor distortion will occur in the case of elongation by breaking by the broken degeneracy, and that is done by stabilizing the d orbital with a z component. So if I am stabilizing or lowering the energy of the d orbital have with z component, it means that my dz square will be lower in energy in comparison with my other d orbitals. Similarly here, okay, so this will be dxy and this will be dxz and dyz. Yes, now as we see that the elongation here is stabilizing the d orbital with the z component, correct? So now if I just simply draw it here, so this will be L metal ligand, and the z component part, since the energy they are stabilized, so obviously they are elongated and hence they are stabilized because of the less repulsion or interaction. Okay, yes, so we can see this type of elongation example in copper 2 plus fluoride. So you can search for it. So basically you see there is a octahedral elongation for the copper fluoride complex. Okay, now again in the case of the compression, what will happen is that the destabilization of this z component will be there, and hence the z component d orbital will be having higher energy, and that is why there it will be in the reverse order. So basically since here z component was stabilized by the elongation, in compression case this will be destabilized, and in that case my dz square will be having higher energy in comparison to the other d orbitals, and that is why I will be having here two orbital having dxz and dyz, and here only one with dxy. Okay, so I am not going in that case. Now the in the case of octahedral complexes, this delta, which is the CFSE, crystal field stabilization energy, is the delta. So this delta plays a very vital role here. We know that this delta is, if it is greater than the pairing energy, so there will be no pairing. No, if the delta is large, so if there is a large delta, then the pairing will happen, and if the delta is smaller, then the pairing energy, then it will be a high spin complex and the pairing will not be there. Okay, so in keeping those things in mind, we simply define the electronic configuration of my T2G and EG orbital in the octahedral field, and depending upon those electronic configuration, so Jahn-Taylor distortion are seen wait okay with the unsymmetrically filled d orbital. So the case that I am telling you here is the okay, so I simply just give you one example. So in example of small delta, that is high spin, so D7, D6, D9, D1, D2, D4, all these will be corresponding having some Jahn-Taylor distortion, but the most stronger Jahn-Taylor distortion will be seen in D9. So I will just write it down here. So in the case of D9, you see that the unsymmetrically filled EG orbital, and hence it shows me some strong Jahn-Taylor distortion. So I think okay, so let's move to our problem. So we have to find out the complex sign which will show me the strong Jahn-Taylor distortion, and so all of them are having H2O as a ligand, and all the four options are octahedral complex. So we know that this H2O is a low field ligand, and it will simply show me small delta value, give me some small delta value. So in the case, I can simply write down the electronic configuration 3D1, 3D4, 3D7 and 3D6 with the corresponding given metal complex. And simply I can write it down here, the T2G and EG electronic configuration, how the electron will be there in the T2G and EG orbital. So in the case of to find out the strongest Jahn-Taylor distortion shown by which complex is to find out the most unsymmetrical EG orbital. So we see that here the most unsymmetrical EG orbital is this. Okay, so this complex chromium H2O6 2 plus, this complex will be showing the strongest Jahn-Taylor distortion. So my option number A here. So this option is the correct option which will be showing the strong Jahn-Taylor distortion. So if you guys have any doubt, you can ask. So moving to the next problem, So this is a 2014 chemistry question number 40. This question states that among the following, the metal carbonyl species having the highest CO stretching frequency is. So we are given with 4 options of metal carbonyl, and we need to find out which one is having the highest CO stretching frequency. So so before jumping into the correct option, I would like you to comment your correct to according to you which one is the correct option. Okay, so just type it in the chat box. So I will be discussing the basic. So you can type your answer there. I will see it later. Okay. So metal carbonyls have a very nice history behind them. The discovery and so their discovery was done by Ludwig Mond in 1884. So he observed in a nickel refining factory that the nickel walls were being eaten away by the CO gas which was used for the nickel refining. So it was basically that the nickel powder in a stream of a CO, carbon monoxide gas. In that process, the nickel powder was basically converting into some metal carbonyl. So it was the compound that was first formed as a or known as a metal carbonyl was the nickel CO4. Okay, so this was the first metal carbonyl was found, and this is what is now known as the Mond process, which is famous for nickel refining. Okay, so this is the history behind metal carbonyl discovery. Now, talking about this CO, that is the uh, ca- carbon monoxide, this particular ligand is very special. It has two type of bonding interaction. First is the sigma donation. So the sigma donate. So it donate the sigma bond from its carbon to metal. Okay, by using the carbon lone pair. Okay, and now for the second, what it does that it accepts electron in the pi antibonding orbital from the d pi metal orbital. So it get back some back bonding, or we call it as back pi bonding. So this is the back pi bonding between the metal and the carbonyl. So you see that there is a sigma bond formation between a carbonyl and metal, and then there is a back pi bonding between the metal d pi orbital and the pi antibonding of the carbonyl carbon. Okay, so there, because of this particular back pi bonding, there is a direct effect of the CO stretching frequency, which get affected by this back pi bonding directly. Okay, so logically, if you see that this metal, yeah, so this metal and this carbonyl. Okay, so logically, if you see that there is a back pi bonding from metal to the carbon, so this carbon which is accepting electron from metal, so this back pi bonding will be directly if this is a strong back pi bonding, then this will weaker the CO bond, and hence it will be the weaker, there will be CO stretching will be weaker. Okay, frequency will be in a weaker region. Okay, So here I have shown in the two diagram the cases that I have just discussed here. Case 1 where my CO to metal sigma donation, and in case 2 from metal to CO pi donation. So from CO to metal sigma donation we see that this is the carbon lone pair, as you are just seeing here. This is the carbon lone pair, okay, and this is oxygen lone pair, and these are the metal and these are the metal D sigma bond. For the metal to CO pi donation, we see that these are the metal d pi orbital, and these are the carbonyl pi antibonding orbitals, and you see that there is a back pi donation here happening. So this is a metal to CO pi donation. Okay, so I will just write the statement here. Since the metal to CO pi donation pi back bonding involves pi donation from the metal d pi orbital to a pi antibonding orbital of a CO bond, there is a significant shift of the mu CO stretching. Stretching frequency. Towards the lower energies observed. So this is all we are saying, the lower frequency of CO stretching are all with respect to the free CO, which is 2.2143 centimeter inverse. Okay, now let's so for this case let's find out the charge on the metal. So the charge on the metal, since CO is a neutral, it carries a negative charge, so this will be -6 equal to +1. So this will be 6 plus 1 . Okay, and here plus 7 plus 6 plus 5 and plus 2. So I can see that okay, Shikha have written that A option because of the less electronic density on the metal, and that is actually correct because simply you can just look into here that the logic basically here that if the sigma bond formation is there, but in the case of the back pi donation, so the stronger is that this donation, the weaker will be the CO stretching, because the stronger bond between the metal and the carbonyl, the weaker will be the bond between the carbon and oxygen. Okay. And the frequency of the CO stretching will be in lower range. Okay. So in the case of my metal having low electron density, that is in the case my metal having a high positive oxidation state, or the charge, positive charge on my metal complex, on my metal. So basically the option number A, where my manganese have oxidation state of +7, so the back pi donation become almost negligible. So in this case the low back pi donation, this creates the stronger CO bond, and hence there is a higher CO stretching frequency observed in the case of manganese complex. Okay, so the correct option for this particular problem is option number A. So any doubt? Okay, we have this is a fairly nice problem. The another problem, question number 42, that you are seeing on your screen. So this particular problem, if you look try to solve by using the magnetic moment formula. Okay, so by using this particular formula, if you try to solve, you will be, I think you will get stuck between the two answer of option B and C, where you will find that there is unpaired electron there is equal to 1 for both the case B and C. So in that particular case you have to be now try look into which one be having more magnetic moment than the other one. So I think I will leave it here for today, and I will urge you to look into the problem, and you can also try to solve this particular problem from 2014, question number 42. Okay, so yes, and the another problem was very interesting to me was the question number 44, that I will discuss in the next live session again. So this magnesium 2 plus ion is preferred in photosynthesis by chlorophyll because. So the correct option I am not going to tell you now, but it is fairly interesting problem. So you can also have a look into this one and this 42 and 44. Okay, so if you guys have any doubt from today's live session, and since I so today is 24, so wait, so today is 24 and I think only, okay, so you were saying, Shikha, that we have in our gate portal live session phase 2 chemistry. Okay. So your paper date is on what February?
5 February, ma'am.
5 February. So
Yes, ma'am.
I think this 11th and 12th week will not be there because they have asked me to do the live session up to 31st of January only. I think so. Today only the another week is there. Okay. So okay, let's see, because already after the week 11, the 12th week will be, so you guys will already be done with your paper. So I don't know why they have given the date. It's okay. So have you got those phase 1 live recordings?
No, ma'am.
Not yet. Okay, so I have asked them to upload. I don't know why they have not uploaded it yet. Yeah, it's not there. Okay. So any specific request if you have for the last live session, then you can take your time. You can email me also later if you want. Okay.
Yes, ma'am. Let me think.
Yeah, if you have any specific topic or any specific request in the last live session, then I think just email me till Saturday at least. Okay. So thank you so much. I will end the live session for today.
Okay, ma'am. Thank you.
Yeah.